Hello my friends and welcome back to the You Can Do TV channel. Inside Caterpillar's high-performance hose manufacturing plant, production is organized around precision, process control, and system reliability. The 275,000 square foot facility operates multiple spiral winder lines, including 50-foot and 250-foot configurations, designed to build complex, multi-layer hydraulic hoses at industrial scale. Weekly throughput includes tens of thousands of pounds of rubber compound and wire, reflecting the material intensity required for high-pressure hydraulic applications used across Caterpillar equipment worldwide. At the core of hose performance is wire lay geometry. Each foot of finished hose contains hundreds of linear feet of high-strength steel wire, applied in carefully controlled spiral layers. Rubber and wire are alternated through successive winding stages, with layer count and placement directly determining pressure rating, fatigue resistance, and service life. Proprietary winding tooling is used to maintain uniform wire tension and spacing, minimizing the risk of leaks or structural failure. Hose and couplings are engineered as a matched system. X-ray inspection is used to verify outer diameter and layer alignment, ensuring proper coupling interface and retention under load. Material flexibility is achieved through coordinated rubber formulations, wire selection, and CAD-driven design. Environmental control within the plant limits temperature and humidity variation, reducing premature curing and compound instability. Cleanliness standards are enforced throughout production to prevent contamination, a critical factor in hydraulic system durability and performance. Follows a structured technical process focused on pressure integrity and material stability. Manufacturing begins with compound mixing, where formulations are prepared for specific mechanical and chemical requirements. Inner tubes are extruded, then reinforced with braided or spiral wire layers to achieve the required pressure rating. An outer rubber cover is applied for abrasion and environmental resistance. Vulcanization under controlled temperature and pressure finalizes material properties. Finished hoses are cut, assembled, and pressure tested to verify performance and compliance with international standards. The mandrel-built industrial rubber hose manufacturing process demonstrated by JYM follows a precise, length-controlled, and material-intensive workflow designed for high-pressure and heavy-duty applications. Production begins with the preparation of a rigid steel mandrel, which defines the internal diameter and straightness of the hose. Rubber compounds are then applied in multiple layers, starting with the inner tube, followed by reinforcement layers such as textile cords or steel wire, depending on pressure requirements. Each layer is carefully wrapped to maintain uniform thickness and concentricity along the full length, which can reach up to 61 meters per hose. An outer rubber cover is added to provide abrasion, weather, and chemical resistance. Once built, the hose assembly is wrapped or taped to control expansion. After curing, the mandrel is extracted, and the hose undergoes dimensional and quality inspections. Established in 1987, BKT's development is defined by the progressive buildup of technical capabilities in off-highway tire manufacturing. Production systems evolved from conventional processes to highly automated lines supported by vertical integration, including in-house carbon black production. Engineering activities are centered on material science, tire architecture, and performance validation. Research and development functions support continuous optimization, from raw materials to finished products. Manufacturing operations also integrate energy efficiency measures, with renewable power contributing to plant electrical demand. These technical and process-driven foundations support large-scale production for agricultural, industrial, and OTR tire applications. Hegi Wire and Strand manufactures high-strength steel wire and strand products for structural and pre-stressing applications. Production covers PC wire ranging from 4.00 to 7.50 mm, and PC strand sizes from 9.30 mm up to 20.00 mm, including die-form strands in the 15.20 to 18.00 mm range. The portfolio also includes compact strands, unbonded strands, PT strands, and stay cables used in bridge, building, and infrastructure systems. Manufacturing processes are certified to ISO 9001 to 2015 standards and emphasize mechanical consistency and long-term performance. Dedicated stress relaxation beds allow controlled testing over 1,000-hour periods to verify creep and relaxation behavior under sustained load. These tests support compliance with pre-stressing specifications and ensure predictable structural performance in service. The remolded tire manufacturing process, as demonstrated by International Tires, is a highly controlled industrial operation that restores worn tires to serviceable condition by reusing structurally sound casings and applying new tread rubber through precision engineering techniques. This process emphasizes material efficiency, safety, and consistent performance. The workflow begins with casing collection and inspection. Used tires are carefully examined to determine whether the internal structure is suitable for remolding. Visual inspections are combined with non-destructive testing methods, such as chirography, pressure testing, and internal probing to detect hidden damage, separations, or fatigue in the casing. Only tires that meet strict structural criteria are approved for further processing. Once accepted, the tire undergoes buffing and surface preparation. Specialized buffing machines remove the worn tread rubber and precisely machine the tire to a specified profile, diameter, and surface texture. This step is critical, as it ensures uniformity and provides the correct bonding surface for the new rubber. Any minor injuries exposed during buffing are repaired using reinforced rubber compounds and patching systems designed to restore casing integrity. The next phase is tread building. In the remolding process, uncured rubber is applied directly to the prepared casing. This rubber is carefully extruded and wrapped to the required thickness and profile, forming the foundation of the new tread. The tire is then placed into a mold that contains the final tread pattern. This distinguishes remolding from simple retreading, as the tread design is fully formed during curing rather than being pre-shaped. The tire then enters the vulcanization stage, where heat and pressure are applied inside the mold. During this process, the rubber chemically bonds to the casing while the tread pattern is simultaneously formed. Vulcanization parameters, temperature, pressure, and time are tightly controlled to ensure optimal adhesion, durability, and wear resistance. After curing, each tire undergoes finishing and quality inspection. Excess rubber is trimmed, markings are applied, and the tire is subjected to final inspections. These include visual checks, balance verification, pressure testing, and uniformity assessment to ensure the remolded tire meets regulatory and performance standards. The final result is a remolded tire that delivers reliable structural strength, consistent traction, and extended service life. When produced under strict technical controls, remolded tires offer a cost-effective and environmentally responsible alternative to new tires, particularly for commercial and industrial applications where durability and sustainability are critical. The Flat Track LTRE is a tire force and moment measurement system designed for high-load, high-speed testing of light truck, SUV, and racing tires. With dual spindle torque and lateral force capability, it enables precise evaluation of traction, cornering, and transient response. Operating at roadway velocities up to 320 km per hour, the LTRE applies radial and lateral forces up to 30,000 N and torque levels up to plus or minus 10,000 Nm. Advanced dynamic control supports slip angle, camber, and slip ratio sweeps, including sinusoidal inputs for both driving and braking. These capabilities allow repeatable characterization of tire performance across a wide range of operating scenarios. Drilling and blasting remain fundamental techniques for rock fragmentation in construction and aggregate production. Modern practices trace their origins to the mid-19th century, when explosives and blasting caps enabled controlled rock breakage for infrastructure development. Today, borehole drilling is performed using track-mounted rigs equipped with rotary percussive systems or down-the-hole hammers, selected based on rock hardness, depth requirements, and site conditions. Drill rods typically range from 10 to 20 feet and are added sequentially to reach borehole depths commonly between 30 and 60 feet, with deeper holes drilled when required. Compressed air is used to clear cuttings from the hole, maintaining drilling efficiency. Production rates vary widely, generally between 20 and 100 feet per hour, depending on geology and equipment. Blasting utilizes commercial explosives such as ANFO and emulsions. Emulsions are pumped directly into boreholes, particularly effective in wet conditions, while ANFO is applied in dry holes. Detonation is initiated using primers, boosters, and millisecond delay detonators to control fragmentation and rock movement. Successful outcomes depend on detailed planning, accurate drilling, and alignment with geological conditions. In the rugged Middleback Ranges of South Australia, what was once considered iron ore waste is being given a second life. SIMEC, mining's 700-ton-per-hour wash and beneficiation plant, stands as a clear example of how smart engineering can unlock hidden value at scale. Designed to process overburden grading just 43 to 52% iron, the CDE-engineered solution transforms this low-grade material into premium products ready for market. At the front end, an M4500 wash plant handles up to 700 tons per hour, cutting and classifying material at 5/32 inch before feeding dedicated lump and fine circuits. AgMax scrubbing units and jig-based gravity separation recover high-quality lump ore exceeding 63% Fe, while cyclones and spiral separators upgrade fines to more than 60% Fe. Supported by efficient water recycling systems and an extensive conveyor network, the plant has already converted over 17 million tons of waste into high-grade iron ore, proving that innovation can turn yesterday's discard into today's resource. Acciaieria di Verona operates as an integrated steelmaking site where scrap metal is transformed into finished long products through a sequence of tightly coordinated industrial processes. The workflow begins in the Parco Rotam, or scrapyard, where incoming ferrous material is received, sorted, and prepared to ensure chemical consistency before melting. This controlled feedstock is essential for maintaining stable metallurgical conditions downstream. Inside the steel plant, electric arc furnaces convert the prepared scrap into molten steel, with composition and temperature continuously monitored and adjusted. The liquid steel is then cast into semi-finished billets, forming the foundation for subsequent rolling operations. From here, production divides into dedicated rolling lines, tailored to specific product types. The laminato vergella is designed for high-speed rolling of wire rod, where precise control of deformation, cooling, and coiling determines surface quality and mechanical properties. In parallel, the laminato bar focuses on bar products, rolling billets into defined cross-sections for structural and industrial use. Each mill is optimized for dimensional accuracy and repeatability. Downstream, lavorazioni a freddo complete the production cycle. Cold processing operations, such as straightening, cutting, drawing, and finishing refined tolerances, improve surface characteristics, and adapt products to customer specifications. Together, these integrated departments form a continuous industrial system, linking scrap recovery, steelmaking, hot rolling, and cold finishing into a single, efficient production flow. Forgia operates as a heavy forging manufacturer, supplying components to global companies across energy, marine, aerospace, steel, and mechanical engineering sectors. Tomperdayan Vesa. The facility is equipped with two independent 500-ton forging presses, enabling the manufacture of forged components weighing up to 25 tons. The production cycle begins with material transport and controlled heating in industrial furnaces to achieve uniform forging temperature. Heated billets are then forged under high press forces to refine grain structure and achieve required geometry. Production is centered on large, open die and shaped forgings used in petrochemical systems, wind power structures, nuclear applications, and high-load industrial assemblies. Subsequent machining operations ensure dimensional accuracy and surface quality according to technical specifications. Controlled cooling completes the process, stabilizing mechanical properties and preparing components for inspection, testing, and downstream integration. The Escondida Growth Site tour in Chile provides a technical overview of large-scale mine expansion activities. The project focuses on increasing material handling and processing capacity through new infrastructure, upgraded systems, and coordinated construction sequencing, reflecting the complexity and scale required to support long-term copper production in one of the world's largest mining operations. Before a single steel plate reaches the strength, dimensional accuracy, and performance demanded by modern industry, It must pass through a long and tightly controlled sequence of industrial processes. Altos Hornos de Mexico, AHMSA, operates a fully integrated steelmaking chain that covers every stage from raw material extraction to finished steel products. Iron ore and metallurgical coal are sourced from company-owned mines, ensuring consistent input quality. The iron ore is transported as slurry to the pelletizing plant, where it is filtered, dried, mixed with binders, and formed into pellets. These pellets are heat-hardened at high temperature before charging into the blast furnaces. In parallel, coal is processed in coke ovens, where it is baked under oxygen-free conditions to produce coke, the primary fuel and reducing agent for iron making. Pellets, sinter, coke, limestone, and dolomite are layered into blast furnaces, exceeding 160 feet in height. Hot air is injected at the base, driving chemical reduction reactions at temperatures reaching approximately 1650 degrees Celsius. Molten pig iron accumulates in the furnace hearth and is tapped into torpedo cars, while slag is separated and cooled for reuse as a byproduct. Desulfurization treatments are applied prior to steelmaking to improve metallurgical quality. Pig iron is converted into steel using both basic oxygen furnaces and electric arc furnaces. In the BOF route, molten iron and scrap are refined by high-purity oxygen injection, reducing carbon content and removing impurities. In the EAF route, graphite electrodes supply high electrical energy to melt scrap and iron units. Alloy additions and secondary metallurgy, including vacuum degassing when required, allow precise control of chemical composition. Liquid steel is transformed into slabs through continuous casting, where controlled cooling produces uniform internal structures. The slabs are reheated and processed through hot rolling mills to produce plates, sheets, and coils. Subsequent pickling, cold rolling, annealing, and temper rolling refine thickness, surface quality, and mechanical properties. Additional operations include tinplate production, structural shape rolling, and finishing lines, supported by integrated power generation, industrial gas supply, and water treatment systems to ensure stable, continuous operation across the entire steelmaking process. GSP suspension and steering components are manufactured through a sequence of tightly controlled forming, machining, assembly, and surface treatment processes focused on dimensional accuracy and functional reliability. Production begins with precision forging of suspension housings, where appearance, geometry, and material flow are controlled to meet structural requirements. Ball joints, as critical load-bearing elements, are produced using cold deformation processes to enhance stability, followed by quenching and tempering. Selected assemblies undergo high-frequency induction hardening to improve wear resistance in high-stress zones. Ball seats, a core element of suspension systems, are manufactured from engineered polymer materials such as DuPont 500P using automated injection molding equipment. Vulcanization parameters, including temperature, humidity, and cycle time, are strictly regulated to ensure material stability and consistent performance. Automated welding robots are used to control weld location and penetration, improving joint repeatability and mechanical strength. Surface protection is achieved through a fully automated electrophoretic coating line, applying a uniform layer that enhances corrosion resistance of suspension components. Ball housings are produced on dedicated automated lines that maintain strict dimensional tolerances. Assembly operations follow standardized procedures across multiple lines, supporting high-volume output with controlled variability. For aluminum control arms, production relies on multi-stage automated forging using high-capacity presses, followed by heat treatment, magnetic particle inspection, surface polishing, and automated acid cleaning. Each component undergoes functional and dimensional testing before release, with process data fed back into upstream manufacturing stages to support continuous technical optimization. GSP automotive wheel hub assemblies are produced through a tightly controlled multi-stage manufacturing process that integrates heat treatment, precision machining, surface finishing, automated assembly, and in-depth inspection. The process begins with finish lathing of the outer flange to establish base geometry, followed by quenching to achieve the required hardness and wear resistance. Both the outer and inner flanges then undergo tempering, relieving internal stresses and stabilizing mechanical properties before further machining. After heat treatment, the outer flange is subjected to final lathing to restore dimensional accuracy. Drilling operations create mounting and fastening features, followed by support position grinding to ensure concentricity. The steel ball raceway and roller raceway on the outer flange are ground with high precision, then superfinished to reduce surface roughness, improve load distribution, and extend bearing service life. In parallel, the semi-inner ring is processed through an automatic machining line. Flat surface grinding establishes axial accuracy while raceway superfinishing refines contact surfaces. All machined components pass through demagnetization and cleaning stages to remove residual magnetism and contaminants that could affect bearing performance. The inner flange undergoes spline broaching to form the drive interface, followed by drilling. Eddy current inspection is applied to critical components to detect surface or subsurface defects before assembly. Steel balls are automatically filled into the cage, with online inspection systems verifying quantity and placement in real time. Final assembly includes seal installation, semi-inner ring assembly, and clearance inspection prior to spin riveting. After riveting, eddy current inspection is repeated to confirm structural integrity. ABS rings are magnetized and inspected for signal accuracy. Final quality assurance includes metallographic analysis, outer diameter inspection, roundness testing, and clearance verification in the test center, ensuring each finished hub meets strict performance and durability requirements. Hartex Rubber operates an integrated tire and tube manufacturing workflow, covering material preparation, forming, assembly, curing, and validation. Production begins in the mixing plant, where compounds are prepared for tube and tire lines. Calendaring, bias cutting, trit extrusion, and bead grommet preparation define the primary component forming stages. Tire building combines these elements into green tires, which are then vulcanized through controlled curing processes. Finished products undergo inspection and static balancing for two-wheeler tires before release. Quality assurance is embedded throughout production, supported by raw material testing, plunger testing, wobble testing, and endurance testing to evaluate durability and structural integrity. In-house mold designing supports dimensional control and repeatability during curing. Manufacturing operations are complemented by process-level resource management, rooftop solar generation, controlled steam production, nitrogen generation from air, condensate recovery, and dry ice blasting for mold cleaning reduce energy, water, and chemical consumption. Waste streams are managed through material reuse, recycled water systems, and biomass utilization, integrating production efficiency with environmental control across the facility. The Central Black Sea Rubber Group follows a structured industrial production flow designed for consistency and technical precision. Operations begin in the raw materials area, where rubber compounds are carefully prepared and mixed to achieve the required mechanical properties. The material then moves into the molding section, where calibrated heat and pressure form each component to its final shape. CNC machining and lathe processes support production by manufacturing and maintaining high-precision molds and metal inserts. After molding, parts are cut and deburred to remove excess material and ensure smooth, accurate edges. Where required, painting and surface finishing are applied for protection or functional performance. Quality control is carried out at multiple stages, checking dimensions, surface condition, and material stability. Once approved, finished components are packed, labeled, and transferred to logistics for organized storage and distribution. Industrial Packaging Limited S-Fiber drum production is a mechanically controlled process designed to deliver consistent strength and cleanliness for chemical and pharmaceutical applications. Manufacturing begins with the delivery of raw materials, including large paper coils and bulk adhesive, which are staged for continuous processing. Paper is unwound from a single roll, coated with adhesive, and wound under pressure into multi-layer cylinders, typically up to 7 plies, forming rigid tubes approximately 8 feet long. These cylinders are transferred onto overhead conveyor racks that circulate through the plant, allowing sufficient drying time for adhesive curing. In parallel, steel rims and lever clamps are prepared, cut to precise lengths, and butt welded to ensure dimensional accuracy and joint strength. Once dried, the cylinders return to the line, where they are cut to length and fitted with a reinforced base rim. Mechanical crimping embeds the steel rim into the fiber wall, increasing load capacity. Top rims are pressed in using similar methods. Final inspection relies on automated visual systems to meet strict cleanliness and quality requirements before closure assembly. A day in the rubber compounding industry follows a tightly controlled technical workflow, where material consistency is built step by step. The process starts with an automatic dosing system that precisely meters small chemical additives, ensuring formulation accuracy and repeatability. Every raw material is tracked through full traceability systems, allowing each batch to be linked to specific recipes, processing conditions, and quality records. Compounding continues in open mixers, where polymers, fillers, and additives are processed under controlled temperature and shear conditions to achieve uniform dispersion. Once mixed, the compound moves through batch-off drying and unloading, stabilizing the material before downstream handling. Packaging is completed through continuous strip or classic strip formats, depending on customer and processing requirements, while traction systems maintain steady material flow and dimensional consistency. Throughout the day, critical material properties are monitored and verified. Rheology testing evaluates flow behavior during processing. Hardness checks confirm final compound stiffness, and density measurements ensure formulation accuracy. Together, these controls define a disciplined industrial environment, where rubber compounds are produced to meet exact technical specifications. The Tamberline removable drum process is organized as a sequential refurbishment workflow focused on restoring steel drums for reuse under controlled industrial conditions. The operation begins with the removal of existing lids, followed by mechanical dent correction to recover drum geometry. Deformation in the drum body is corrected through either manual or automated forming stations, depending on damage severity and throughput requirements. Drums then pass through a residue burn-off furnace, where internal contaminants are thermally removed. This step ensures that oils, chemicals, or residual materials are eliminated before surface treatment. After thermal cleaning, the drums are subjected to steel shot blasting, using controlled granula projection to remove scale, oxidation, and surface irregularities while creating a uniform profile for downstream processes. Dimensional recovery continues with expansion operations to restore roundness, followed by bottom rolling through a calandra system to re-establish structural integrity at the base. Once mechanical restoration is complete, drums enter the painting stage, where protective coatings are applied to improve corrosion resistance and extend service life. Final assembly focuses on the removable closure system. New lids are formed using dedicated molds, ensuring consistent geometry and sealing surfaces. Gaskets are installed to provide reliable containment performance. Each stage contributes to returning used drums to functional condition, combining mechanical reconditioning, thermal treatment, and surface finishing within a structured industrial refurbishment line. Steel drum production at TV Daikin starts with large steel coils fed into an automated forming line. The steel is cut and rolled into cylindrical drum bodies, then passed through corrugation machines to create reinforcing ribs. Separate lines stamp and form the drum lids with precise sealing profiles. The assembled drums move through surface preparation and automated painting systems, where different colors are applied and cured to meet durability and corrosion resistance requirements. Steel drum manufacturing begins with flat steel sheets that are cut to precise dimensions for drum bodies and ends. The body blanks are rolled into cylindrical shells and longitudinally welded to form a rigid structure. Drum ends are stamped and flanged to create strength and sealing surfaces. The shells are then expanded and seam welded to the top and bottom ends. After welding, each drum is leak tested, cleaned, and surface treated. Final stages include coating or painting, curing, and dimensional inspection before packaging and shipment. The CFT Group Complete Lube Oil line is configured as an integrated, end-to-end system designed to manage filling, sealing, labeling, and palletizing with a high level of automation and process control. The line combines modular equipment to accommodate multiple container formats, from small packages to 200-liter drums, while maintaining consistent accuracy and throughput. At the core of the system are lube oil filling and capping monoblocks, including the MRV 9/5 plus VP3 and MRV 24/1 plus VP8 models. These units integrate filling and closure operations within a single frame, reducing transfer points and improving synchronization. Filling parameters and cycle control are managed through operator panels, allowing precise adjustment for different oil viscosities and container specifications. For large format packaging, the 200-liter drum line begins with an automatic empty drum magazine capable of storing up to 4,000 drums in a reduced footprint. Drums are fed automatically and guided through an orienting device that aligns containers with off-center filling holes. An unscrewing station removes 1-inch bungs and transfers drums onto the conveyor without manual intervention. Final filling is performed on electronic scales interfaced with tare systems to ensure accurate net weight control. Once filled, drums pass through an automatic sealing station that verifies correct closure application. Labeling is applied in line before drums are transferred to an automatic robotic palletizer. The palletizing system is designed to handle single and double pallet configurations, completing the line with stable, repeatable stacking. Across the entire process, automation reduces handling variability while improving safety, accuracy, and traceability. The result is a continuous lube oil packaging system engineered for industrial-scale reliability and controlled production flow. The MacroPack AF/2 is a two-head aseptic filling system developed by CFT Group for high-capacity, hygienic food packaging applications. Designed for flexibility, the system is capable of handling multiple aseptic formats within a single platform, supporting 1,000-liter aseptic bags in bins, 200-liter aseptic bags in drums, typically arranged as 4 drums per pallet, and, as an option, 5 to 20-liter aseptic pouches. The filler operates under fully aseptic conditions, with controlled product paths, sterilized filling heads, and sealed transfer interfaces to protect product integrity throughout the filling cycle. Dual filling heads enable higher throughput while maintaining precise volume control and repeatable filling accuracy across different container types. Format changeovers are engineered to be efficient, allowing the system to adapt to varying production requirements without extensive downtime. Integrated automation manages filling sequences, head positioning, and container handling, making the MacroPack AF/2 suitable for industrial food processors requiring scalable aseptic packaging with consistent hygiene and process reliability. Tank 24 construction follows a structured sequence of civil, mechanical, and welding operations designed to deliver a large-capacity storage unit with controlled tolerances and long-term integrity. The process begins with site preparation and foundation works, including grading, reinforced concrete placement, and anchor bolt installation to establish precise alignment. After the foundation reaches design strength, bottom plates are set, welded, and inspected to form a leak-tight base. Once the lower shell courses are erected, a crane is mobilized and positioned inside the tank. This internal lifting strategy allows shell plates, roof members, and internal components to be handled vertically within a confined footprint, improving control and reducing external lift constraints. Shell erection then proceeds course by course, with vertical and circumferential welds completed using qualified procedures and verified through non-destructive testing. Internal structures such as stiffening rings, nozzles, and manways are installed as the shell rises. Roof components are assembled using the internal crane before final positioning and attachment. The construction sequence concludes with surface preparation, coating application, and hydrostatic testing to confirm structural performance and leak integrity under design loads. The Master C-Block is an automatic filling and seaming monoblock system developed by CFT Group for canning operations in small to medium-sized breweries. The system integrates filling and seaming within a compact footprint, delivering controlled performance in space-limited production environments. Operating at capacities from 3,000 up to 15,000 cans per hour, the unit uses flow meter filling technology to achieve high fill accuracy and repeatability. Oxygen pickup is tightly controlled during the filling process, supporting product stability and shelf life. The filler can be configured with up to 24 PLC-controlled filling valves, allowing precise management of flow rates and filling sequences. Seaming components, including chucks and rolls, are engineered for consistent seam formation and dimensional stability. Optional automatic dummy caps support hygienic operation and controlled startup and shutdown procedures. GSP Automotive is built on a strong belief in the power of manufacturing through vertical integration. By controlling each stage of the production process internally, GSP ensures consistent quality, cost efficiency, and reliable delivery for customers worldwide. Currently, GSP utilizes approximately 70% of its total production capacity across more than 3.5 million square feet of advanced manufacturing facilities located throughout China. This strategic reserve of capacity allows GSP to respond quickly to market demand while maintaining strict quality control. From raw material processing to final assembly and inspection, GSP manages every critical step in-house. This end-to-end manufacturing capability enables the company to deliver high-quality rubber-to-metal RTM parts at competitive pricing without compromising performance or durability. Each component is manufactured using state-of-the-art equipment and advanced production techniques, ensuring excellent bonding strength, dimensional accuracy, and long-term reliability. Quality is a cornerstone of GSP's manufacturing philosophy. As a global leader in the automotive aftermarket and powersports industry, GSP holds numerous international certifications that demonstrate compliance with the highest industry standards. These certifications reflect the company's commitment to continuous improvement, process control, and product consistency across all production lines. Innovation also plays a vital role in GSP's success. Supported by an extensive research and development team, GSP RTM products are designed and engineered by experienced professionals with deep industry knowledge. Engineers and technicians work closely to optimize fit, form, and function, ensuring that every part meets or exceeds original equipment specifications. Advanced testing and validation procedures are applied to guarantee performance under demanding operating conditions. GSP takes pride in delivering durable, long-lasting RTM solutions that customers can trust. By combining vertical integration, cutting-edge technology, rigorous quality standards, and engineering excellence, GSP has established itself as a world-class manufacturing partner. Whether serving the automotive or powersport market, GSP continues to be a leading global resource, providing dependable products that support safety, performance, and customer satisfaction. Custom rubber components are manufactured to support a wide range of industrial segments where material performance and dimensional control are critical. In the medical sector, elastomer parts are produced from controlled, medical-grade compounds for use in diagnostic equipment, fluid handling, and disposable and reusable devices. Food and beverage processing applications require FDA, 3A, and NSF-compliant materials, including metal X-ray detectable rubber, used in contamination detection systems. Oil and gas operations represent one of the most demanding segments, requiring elastomers with resistance to high pressure, rapid gas decompression, and sour gas exposure. Fluid power and industrial automation rely on tight tolerance seals for pneumatic and hydraulic systems, valves, and electronic controls. Aerospace and defense applications require compounds qualified to military specifications for landing gear, refueling systems, and control assemblies, where consistent material behavior and traceability are essential. A 4-ton tire change is a carefully sequenced maintenance operation focused on safety. The process begins with isolating the machine and relieving residual pressure before controlled lifting is performed. The wheel assembly is then loosened and removed using high-torque tooling designed to manage fastener preload without inducing structural stress. A heavy-duty forklift is used to lift and extract the wheel assembly from the machine. Alignment during installation is critical. The replacement tire and rim are positioned with precision to ensure proper seating, followed by staged torque application to meet specification. Final checks confirm load distribution, fastening integrity, and readiness for return to service.